Okay, let's look at question 11. This is for Physical Sciences grade 11, a question based on electric circuits. Question 11, 11.1. A number of meters and resistors are connected as shown in the diagram. This is the diagram that they are referring to. A 3.0 volt battery is connected to the terminals X and Y. So we are given a diagram and they are telling us that a number of meters are connected. So which meters are those that they are referring to? They are referring to this voltmeter. There's also this voltmeter here. So this voltmeter is voltmeter V1. This voltmeter is voltmeter V2. And there's also an ammeter. So that is the third meter that they are referring to. They also tell us that they also have a number of resistors. In total, in the circuit, there's about 4 resistors. This resistor here with a resistance of 2 ohm. There's a resistor here with a resistance of 3 ohm. There's a resistor here with a resistance of 3 ohm. And this resistor here with a resistance of 4 ohm. So those are the resistors that they are referring to. So because we've analyzed this, we are in a position to actually answer the question. But there's one last piece of information that they mention. They're saying that there's a battery that is connected across this whole setup. And that battery is connected to the terminals X and Y. So I personally will choose this terminal to be the positive terminal and this to be the negative terminal. It will become clear later why I'm choosing. Somebody else might do it differently, might say, okay, this might be my positive terminal and this will be the negative terminal. Because the question didn't specifically tell us which terminal is positive and which terminal is negative. But we know for every battery, there's always a negative and a positive terminal. The long strand of the battery will be the positive and the short strand would be the negative. The long, the positive, the short, the negative. So they're saying that there's a battery that is connected there. So we can draw this imaginary battery here and say, okay, that battery might be somewhere there all the way to the other terminal. And that battery, they're saying it has a value of 3 volts. So the potential difference from the battery would be 3 volts. Good. Question 11.1.1. Determine the reading on V1. Determine the reading on V1. Where is V1? V1 is this voltmeter over here. Let me just erase a couple of things here, just to open space. So the question is requesting us to determine the reading on V1. We're not doing any calculations, hence it's a 1-mark question. And once you are comfortable with electric circuits, it will be much easier to see these things naturally, but it takes a little bit of practice with doing in different circuits to just see it from the beginning what that potential difference would be. So but I'm gonna take you through a short explanation as how do we determine that potential difference there. So the first thing you need to be aware of is that there are some very interesting properties of voltmeters that we can talk about. So one, voltmeters are always connected in parallel to whatever circuit element, always connected in parallel to whatever circuit element we're trying to determine the potential difference of. Always. The second part is that voltmeters have a high resistance. Remember, resistance just is the opposition to the flow of current. So they have a high resistance. So they oppose the flow of current because their main job is to measure potential difference. Measure potential difference. So wherever you see a voltmeter, one, you'll notice that it's always connected in parallel. One, you should know that it has a high resistance. And last, that yes, it measures the potential difference. So this voltmeter V1 is connected in a branch. Let me take maybe this color, looks nice. This voltmeter is connected in this branch over here. You see. However, if you look at the other circuit elements, your resistors, your ammeters, and the other voltmeters, they are all connected around here. So it appears as though that voltmeter is connected across the whole circuit in a sense. So this voltmeter is connected in parallel to this whole part because it's on a different branch than the rest of the other components in this electric circuit. So that's how we know when things are connected in parallel. They will be connected on a different branch. So this is the purple or light purple branch, and the other circuit elements are connected within this branch here. So essentially, it's telling us that this voltmeter is measuring the potential difference across the whole of this, where I had drawn the dotted lines. It's measuring the potential difference across everything. So this voltmeter measures the potential difference that is going through this entire thing. And the potential difference that is going through that entire thing, where does it come from? The potential difference comes from the battery. And how much potential difference that the battery supply to the whole thing, it supplies a value of 3 volts. So this is why for 11.1.1 you'll say that V1 equals to 3 volts. So this potential difference will measure the potential difference that is supplied by the battery to the whole circuit. I hope that is clear. Just going to erase now, just so that we can open a little bit of space. If we look at question 11.1.2, okay, we are done. Question 11.1.2, it says, calculate the reading on A. What is A? A is this ammeter over here. So we need to find the reading here. Before we do that, let's do a similar thing that we did for voltmeters. What are the interesting things about ammeters? One, they are always connected in series. Always connected in series. The second one, they have very low resistance. So you don't want your ammeter to be resisting current. The moment it does that, it means you won't be able to read or to measure the maximum current. And what is their function? Is to measure the current. So be able to differentiate between these two types of meters that we find in basic electrical circuits. A voltmeter is always connected in parallel. An ammeter is always connected in series. A voltmeter has high resistance. An ammeter has very low to no resistance. A voltmeter measures potential difference and an ammeter measures the current. So those are the qualities of an ammeter. So to now determine what is the current here, we need to just go a step back. We need to understand relationships between or differences between connections that are said to be parallel and connections that are said to be series. How do we determine which elements or which circuit elements are in parallel, which circuit elements are in series? My advice to you is to always follow the current. Follow the current. It will never mislead you. So let's start. Let's follow the current. The direction of conventional current flow. Conventional current flow is always from the positive terminal to the negative terminal. So the direction of conventional current flow is always from the positive terminal to the negative terminal. That's why I wanted to be specific that I choose my X to be the positive terminal and my Y to be the negative terminal. So we have current that is coming from the positive terminal of the battery. See that current is going there. Whoop. Let's call that current I, right? Remember, I said voltmeters have a very high resistance. So there's no current. This current is not all of a sudden going to split itself and go into the voltmeter. No. And that is exactly why they have a high resistance to stop that from happening. So what you then have, that current will just go straight until it reaches this point here. When it reaches this point, it's almost as if it's arriving at a three-way stop. It sees, hi man, there is now, it's no longer a single branch, but this single branch has split into two branches. So let's distinguish those branches. Let's say we have the red branch here. This branch is going through the 2 ohm resistor, through the ammeter, through the 3 ohm resistor. And then it looks, or on the other side, it realizes there's another branch here that goes through the 3 ohm resistor, through the 4 ohm resistor. So it's like, what do I do? When it reaches that point, it's actually going to split. Because these are two separate branches, the red branch and the yellow branch are in parallel to each other. The red branch and the yellow branch are in parallel to each other. Hence, the current will split. Circuit elements, let me write it down. Circuit elements connected in parallel have the same potential difference. But they split the current. So this red branch and the yellow branch are connected in parallel. It means they'll experience the same potential difference. What is the potential difference that they'll experience? It is this potential difference that was measured by V1 that was supplied by the battery. So they will experience the same potential difference of 3 volts. However, they will split the current. That means the current that is going to the red branch will be different. Let's call that current I, versus in comparison to the current that is going to the yellow branch. Let's call this also current I. So those currents will be the same, and I will just be the sum of the two currents. So the total current will start to split when it arrives at that point. We have not answered the question yet. We know what the potential difference is, but what is the current that the ammeter is going to detect or is going to read? So if you look, all the circuit elements, this resistor, this ammeter, and this resistor are all connected in a single branch. And when this happens, we say that they are connected in series. So these 3 circuit elements, the 2 resistors and the ammeter, are connected in series on the red branch. What is something interesting about circuit elements that are connected in series? Let's see. Circuit elements connected in series experience the same current but split the potential difference. Okay, so it means that all these circuit elements here in the red branch will have the same current. So this resistor will have the current I, this ammeter will measure the current I, and this resistor will also have this the current I. So which is the current that got split here at this point. So if we have the potential difference and we have the resistance within the red branch, we can actually find what the current is, which is the same throughout, by using Ohm's law. So Ohm's law, that's question 11.1.2. Question 11.1.2. Yes. We're going to use Ohm's law, which says R equals to V over I. We're looking for I. This means we need to rearrange. So one of the easiest ways to rearrange is just to draw this triangle where you have R equals to V at the top and I at the bottom. This is what we're trying to find. So it means my I, which is the current, I is going to be equals to V at the top. So it will be the numerator divided by the resistance R in the denominator. Fine. We know what V is, but what is R? R, because I said these 2 elements, or all of them actually, are connected in series, and this has no resistance. Ammeters have very little to no resistance. So to find the total resistance within this branch, we'll just say it is RS, R for S for series, which is just going to be 2 plus 3, which is just 5. So it means that my potential difference, I said it's 3. My resistance is 5. If we put this on a calculator, 3 divided by 5, that is going to be 0.6 ampere. So you'll get a mark for this formula, you'll get a mark for the substitution, and you'll get a mark for the final answer. So that's where your 3 marks will come from. Remember, for 11.1.1, the mark was just 1. Let's go to the next question. The next question says to us, calculate, which is 11.1.3. Calculate the reading on V2. Where is V2? There is V2. So what is the potential difference at V2? So we have said that the red branch and the yellow branch are in parallel, meaning they were experiencing the same potential difference that was measured by voltmeter V1 supplied by the battery between the terminals X and Y. If we get into this branch specifically, we see that these two elements, circuit elements, which are the two resistors, are actually connected in series. What did we say about circuit elements connected in series? We said circuit elements connected in series experience the same current but split the potential difference. The same way with the red branch circuit elements. So we have the current I here, the yellow I, as well as the current I over here. They all have the same current. However, their potential difference will be different depending on the magnitude of their resistance. Hence, they say actually determine what is the potential difference across the resistance of 4 ohm. That will essentially be determined or read by this voltmeter V2. So we know we know what the resistance is here. We can find the current, and when we have the current, we can actually find the potential difference. So let's do that. So we'll say the same way as we done earlier, we use this equation that I equals to V over R. So that is question 11.1.3. I equals to V over R. What is V? We said it's 3 volts. What is R? R here, because these two are connected in series, it's going to be RS equals to 3 ohm plus the 4 ohm. How much is that? That is 7 ohm. So it means it's going to be 3 over 7. And that is in ampere. Please note that I'm not rounding it off yet. I'm not converting it to a decimal and rounding it off, because this is not the final answer. For the final answer, we're still going to use our Ohm's law. So R equals to VI, because we need to find what V is, that V2 is. So it's going to be V equals to R multiplied by I. So R multiplied by I. We have what I is. We also know what the resistance is for this resistor. So it's just a matter of substituting. So we say it's 4 multiplied by 3 over 7 amperes. If you put this on a calculator, you'll get a value of 1.71 volts. There's another way of doing this. So let's see what the mark allocation will be like. So you'll get a mark, a mark, a mark, a mark, a mark. Is it 4 or 5? That is 5. So I think that's where the 5 marks will come from. But there's also another way of actually calculating this, where you can say, to find V2, I will say what is the total voltage or potential difference? It's V1 multiplied by the resistance that we are looking for. It's the 4 ohm resistor divided by the total in that branch, which is 4 plus 7, 4 plus 3. So the total potential difference is 3 volts multiplied by 4 over 4 plus 3 is 7. This is the same thing, and you still get 1.71 volts. But looking at the mark allocation, you see here you don't actually use a lot of formulas. But here you've used potentially two formulas. It tells you that ideally they would want you to use this method of Ohm's law to determine the potential difference through V2. Okay, now we are actually ready to go to question 11.2. Question 11.2 is saying a tumble dryer is labeled 220 volts and 2600 watts. So we're given the voltage and the power. The voltage V and the power P. We're given the voltage V and the power P. And question 11.2.1 says, calculate the resistance of the tumble dryer's resistor. So we must find R. So that's question 11.2.1. Given the power, which is 2600 watts, given the potential difference, which is 220 volts, what is R? If you go at the back of your question paper, you'll find one of the power equations is P equals to V squared over R. We have P, we have V, or potential difference, meaning we can actually calculate this. Still the same way, use a triangle where you say P equals to V squared over R. To find R, we simply say R equals to V squared at the numerator divided by P. So what is V squared? It's 220 squared divided what is the power? It's 2600. If you put this in a calculator, you will come to a value of 18 point, let me check, a value of 18.62 volts. If you put this 220 squared divided by 2600. Let's go to question 11.2.2. Calculate the cost of using the tumble dryer for 3.5 hours if electricity costs R1 rand 4 cents per kilowatt hour. So the equation to determine the cost of electricity is not provided at the back of your question paper. However, what you will find is that it's just important for you to know it. Cost of electricity. So memorize it if need be. Use B. To do that, you'll say the power multiplied by the time multiplied by the cost per unit. So we have the power. Our power was said to be 2600 watts. Our time was said to be for a period of about 3.5 hours. And the cost per unit is said to be 1 rand and 4 cents per kilowatt hour. We have everything, it's just a matter of substituting. But before we do that, because here it's given as kilowatt, it means we first need to convert the watts to kilowatts. So if we're moving from watts to kilowatts, we just divide by 1,000. So this will just be 2.6 kilowatts. Even this, to move it from this mixed fraction to a decimal, it's going to be 3.5 hours. 3.5 hours. We have everything, then we are in a position to actually calculate how much will that cost us. Cost of electricity will be, what is the power? We said it's 2.6 kilowatts. What is the time? It's 3.5 hours. What is the cost? Is 1 rand and 4 cents per kilowatt hour. So because everything here is multiply and this division, it means you can just simply cancel. The kilowatt will cancel this kilowatt at the bottom. The hour will cancel the hour there. So the kilowatt in the numerator will cancel the kilowatt in the denominator. Then we are left with 2.6 multiplied by 2.6 multiplied by 3.5 multiplied by 1 rand 4 cents. If you put this in a calculator, you will find a value of about 109 rand 46 cents. So this is the cost of electricity. We've actually come to the end of this question. It was a 16-mark question. If something is not clear, please do let me know, and I'll try to attend to it as quickly as I can. Thank you.